Welcome back to Gradient Daily. Today, we are breaking down a paper accepted at ICLR 25 by Juni Zhang and colleagues titled MonST3. Look at this urban scene. For an autonomous vehicle to navigate safely, it must map moving vehicles and pedestrians in real time. Real-world environments are rarely static, making dynamic scene reconstruction a central challenge in computer vision. Historically, systems have approached this by decomposing the moving scene into subtasks. First, they calculate scene depth. Then, they track optical flow. Finally, global optimizations stitch everything together. This multi-stage pipeline operates like a relay race, passing data sequentially from depth to optical flow to global optimization. But it's vulnerable. If depth estimation stumbles, the error is inherited by optical flow. By final optimization, early inaccuracies compound, outputting distorted geometry. Because these traditional multi-stage pipelines attempt to build explicit motion models on top of fragile geometric foundations, they are brittle. MonST3R offers a different thesis. Dynamic scenes can be modeled without using any explicit motion representations. The authors call this a geometry-first approach. Instead of tracking where pixels go over time, they completely drop optical flow from the equation. The left shows the error-prone traditional pipeline. On the right, MonST3R estimates geometry for each time step independently. By treating every frame as a discrete spatial environment, this flattened architecture prevents cascading errors. A bad calculation in frame 10 is isolated, never corrupting frame 11. MonST3R solves the dynamic problem not by tracking movement better, but by treating moving scenes as a sequence of independent spatial environments. To understand how MonST3R generates these environments, we have to look at its predecessor, Duster. MonST3R is a foundational model designed specifically for reconstructing purely static 3D scenes. Watch this geometric structure attempt to deform. When a static model like MonST3R processes environments that bend or move, its rigid spatial assumptions fail. It lacks the mechanisms to make sense of changing coordinates. The authors bypass this limitation using what we can think of as a flipbook mechanism, adapting the static MonST3R architecture for dynamic environments. Instead of modeling fluid motion between frames, MonST3R extracts an independent 3D point map for each frame. Motion is captured implicitly. Movement is the mathematical difference, or delta, between these sequential snapshots. The architecture doesn't actually learn movement. It learns precise sequential existence, bypassing the need for an explicit motion module. Tracing the MonST3R network architecture, the path flows from input video frames straight to point map generation. Zooming in on the temporal alignment mechanism, the network aligns independent time steps spatially without using optical flow vectors. The mathematical intuition here is correlation. The network aligns frames by matching stable structural features across time, comparing the spatial relationships within the point maps rather than tracking shifting pixels. To support this, the authors introduced video-specific optimizations, streamlining the loss functions to ensure smooth inference on downstream tasks like depth and pose estimation. MonST3R achieves temporal coherence by anchoring discrete geometric spaces to one another. It proves that spatial understanding can override the need for motion tracking. Executing this geometry-first approach requires an enormous amount of data, which brings us to a bottleneck in 4D computer vision, the scarcity of posed video datasets with dense step labels. Training a dynamic model on exclusively static data is like trying to study marine biology using only dead, motionless fossils. You get the structure, but you miss the mechanics of the living organism. This bar chart compares the volume of available static 3D datasets against the tiny fraction of dynamic 4D datasets. To overcome this, the authors identified and curated a few rare datasets containing moving subjects to build their training set. These specific dynamic datasets are mathematically required. Without them, the neural network has no gradient to learn how a camera pose shifts while the subject itself undergoes deformation. The authors used a strategic fine-tuning methodology to train the Duster Foundation on this limited data pool. By carefully modulating the learning rates, they taught the model dynamics without triggering a loss of its core spatial intelligence. MonST3R's results show that strategic data curation can enable a static architecture to understand fluid, dynamic scenes. Transitioning to the empirical results, the team benchmarked MonST3R specifically on its performance in video depth and camera pose estimation. This line chart tracks error rates across benchmarks. MonST3R significantly reduces errors compared to prior multi-stage models, maintaining accuracy where older pipelines break down. We also see reduced processing time. This efficiency comes strictly from eliminating the computationally expensive optical flow optimization phase. But the paper reveals a surprising finding. The targeted fine-tuning process alone enabled the model to perform state-of-the-art feed-forward 4D reconstruction. Look at the visual fidelity of these 4D reconstructions. The model captures complex subject deformation, despite lacking any explicit instructions to track the motion itself. By discarding explicit motion representations, the model produces more accurate, motion-aware geometry. Still, the geometry-first approach has boundaries. We have to ask what happens during extreme occlusion, where a subject is hidden and the point map correlation across frames breaks down. Look at this chaotic movement. Erratic motion risks confusing the independent time-step extractions, creating gaps too wide for the spatial alignment to bridge. Furthermore, relying on such a limited pool of fine-tuning data raises a valid concern. It might bias the model against real-world physics that weren't captured in the training set. These limitations outline future research factors. The next steps will likely involve integrating MonST3R into real-time robotic SLM systems or testing limits in turbulent environments. Here's your summary. First, traditional multi-stage pipelines are brittle. Second, MonST3R extracts independent per-time-step point maps. Third, it overcomes data scarcity through strategic fine-tuning. If this breakdown clarified 4D reconstruction for you, hit the like button, subscribe to the channel, and join us tomorrow for our next deep dive. MonST3R proves that in 4D vision, foundational simplicity scales far better than layered complexity.